42,
Yes, sir.
43,
Present, sir.
44, 45,
Present, sir.
46,
Present, sir.
47, 48, 47, 47, 48,
Present, sir.
49,
Present, sir.
50, 51,
Present, sir.
52,
151.
52, 53,
Present, sir.
54,
Yes, sir.
55, 54 দিলে তাই তো 55, 56, 57, 58, 59,
Sir, এটা 59. Yes, sir.
60,
Present, sir.
61,
Present, sir.
62,
Present, sir.
6 আচ্ছা $45 আর কেউ নেই তো প্রেজেন্ট তো আমি একবার রিপিট করে দিচ্ছি 39 প্রেজেন্ট 41 প্রেজেন্ট 42 প্রেজেন্ট 43 প্রেজেন্ট then is 45 46 present then is 48 49 present তারপর হচ্ছে 51 present 53 54 present 59 60 61 present 62 present ঠিক আছে সো এক সেকেন্ড একটু হোল্ড করো দাঁড়াও হ্যালো হুম আচ্ছা so last day have you seen the presentations have you seen the ওই videography of the things সেখানে কোনো কোশ্চেন আছে all of you have got the links for the videography
Yes, sir.
Yes, sir.
so ওগুলো have you gone through them any doubts regarding them or
স্যার
do
ওই
you-
স্কেল গুলো কি বলছিল মানে B1 B2 স্কেলটা একটুখানি যদি বলে দেন
B1 B2 স্কেল ওটা তো রকওয়েলে আছে বোধহয় রিনেলে তো নেই ওটা আমি আজকে পড়াবো রকওয়েল যেটা আছে রকওয়েলটা আমি আজকে পড়াবো ঠিক আছে আমি ব্রিনেলে যে জায়গাটা বলেছিলাম সেটা নিয়ে কোনো ডাউট আছে কারোর হ্যালো আজকে আমরা আবার ওই ডিসকাশনটা স্টার্ট করছি। এটা এটা দেখো না, হালকা হয়ে যাচ্ছে। এবার ঠিক আছে। So let us start with today's discussion. আচ্ছা, যারা জয়েন করেছে একটু তাড়াতাড়ি বলে দাও তো রোল নাম্বার।
Sir, rule 140.
140.
Yes, sir. Ankit Prasad.
Next.
Sir, roll 155, Krishna Ward.
155. ঠিক আছে। So let's start with the discussion for today. So I hope ওখানে কোনো ডাউট নেই। I will be going through the videos. একবার আমি ওটা প্রেজেন্ট করব, আগে একটুখানি কভার করে নিই, যা যা একটু বলার আছে সেগুলো আগে একটু বলে নিই। দিয়েছি 152 দিয়ে দিয়েছি। সো আচ্ছা, so the call is being recorded. আচ্ছা, সো আমরা যতটা ডিসকাস করেছিলাম, লেটস স্টার্ট ফ্রম দ্যাট। So today we'll be discussing Rockwell hardness testing. ঠিক আছে? So what is Rockwell hardness testing? So as in Brittle hardness testing, you are able to listen to me, right?
Yes, sir.
So as,
Yes, sir.
So as in Brittle hardness testing, we measured the impression shape actually. So we measured the impression diameter D1, D2. So it never referred to the depth of penetration, right? So we didn't measure any depth of penetration of the indenter. So এইখানে দেখো, সো আমি এই যে ডেপথ অফ পেনিট্রেশন, এই ডেপথ অফ পেনিট্রেশনটা আমাকে বলা হয়নি, হোয়াট শুড বি দ্য ডেপথ অফ পেনিট্রেশন এন্ড অল, দ্যাট ওয়াজ নট গিভেন টু আস। সো ইন কেস অফ রকওয়েল হার্ডনেস, what will be measuring is the depth of penetration, P. ঠিক আছে? So in case of Brittle hardness, we measured the diameter of indentation, and in case of Rockwell hardness, we will be measuring the depth of indentation. So in this case, the permanent depth of indentation is measured. So I had discussed in the last class that in case of hardness, so the definition of hardness itself states that it is the plastic deformation. ঠিক আছে? The resistance to plastic deformation. So only the permanent deformation or the plastic deformation that gets formed inside the material that we have to measure. So what is the suitability for Rockwell hardness testing? So it's most accurate than other methods. So whatever are the methods of hardness testing like Brittle, Rockwell, Vickers, shore hardness, many hardness tests are there. So amongst all of them, this one is the most accurate and most widely used. It is very easier to perform, used for most materials except large surface variations. So it is useful for most of the metals that are available in engineering applications. So it's used for relatively softer materials compared to the Brittle hardness test, which is used for harder materials. So Brittle hardness test is mostly used for harder materials, or which are having like quartz shapes actually, quartz grains actually. So in that case, we'll be using the Brittle hardness test, and comparatively softer materials having finer grain sizes, for them we will be using the Rockwell hardness testing. So in Brittle hardness, we applied a single load actually, but in case of Rockwell hardness, we will be applying two loads. So initially we have to apply a minor load or a preload of 10 kg force is applied on the test surface using a diamond or a ball indenter. So a minor load application of this minor load, it was not required during the case of Brittle hardness testing. Why? Because in case of Brittle hardness testing, we never measured the depth of indentation. So whenever you are actually measuring দাঁড়া। কত যে জয়েন করলে তার রোল
157.
ঠিক আছে। সো So whenever we are measuring the depth of indentation on the surface actually, so we have to consider one datum line. When I am measuring the depth actually, one depth or one height whenever you are measuring. So you have to measure the depth starting from some datum line. So that datum line has to be considered. So in order to create a datum line, what we do is we apply a minor load of 10 kg force or a preload of 10 kg force on the surface of the specimen using a diamond or a ball indenter. And this preload or minor load penetrates the surface to reduce the effects of surface finish while measuring. So after holding the preliminary test force for a specified dwell time, the baseline depth of indentation is measured. So let me explain the thing actually. So here you can see the thing diagrammatically. It is taken from InNet itself. So whenever we are measuring a depth actually, so you can understand that on the surface of the specimen, we cannot consider the surface of the specimen as a like regular reference line. Why? Because there are many imperfections, many surface coatings, many darts, dust, many things actually. Rust and all those things. So there are many things on the surface which prohibits its use as a reference line. So for that, what we do is initially we apply a minor load of a certain 10 kg force on the specimen so that it indents a height of say this one. So this one is the initial height. So this one, so it indents a certain height. So this height, it's not written here. So this height, A height, so this height, we call it as this anything like indentation depth, say delta or something. So this delta depth, so this after I indent by a depth of delta, so I have to keep the load there for a certain amount of time. Why? Because this delta will be having two parts, elastic part and plastic part. So I have to allow for certain dwell time so that the elastic part recovers by itself and only the plastic part remains. So whatever is the plastic part remains, so that part, that depth actually, that forms the zero reference line from which I can continue the depth measurements on the surface. So why I am doing this? Because any surface that is having some rust and imperfections like surface coatings and many things actually. So you can do some surface preparations and all. Still, what we do is we apply a minor load of a certain like 10 kgf and all, and then we and whatever is the depth that the indenter is indenting on the surface, that depth we consider that as the zero reference line from where we can start the measurement, say D or T, whatever we say. So the depth of penetration, that we start measuring from this reference line. So initially we have to create one reference line. So that reference line is created by application of this minor load on the indenter. Then what we do is, then we apply the major load. So this completes this part. So part discussion the preload penetrates the surface to reduce the effects of surface finish and other irregularities, and after holding it for a specified dwell time. So why we are holding it for a certain dwell time? Because after the dwell time, the elastic part will vanish and only the plastic part will remain, which will form my basis for future measurement. So this baseline depth of indentation is measured. So now keeping this minor loads, so I want to keep in mind that we are keeping the minor load. So keeping the minor load, now the major load is applied. So what is the major load? What is the value of the major load? That will be coming to it later. So the basic is you apply the minor load, and then keeping the minor load there, you apply the major load. Okay, so this minor load plus major load, that forms the total load on the specimen. And then again, you keep the load for a certain specified amount of time so as to allow for recovery of the elastic part. Now, again, you remove the major load, keeping the minor load there. So whatever is the depth of penetration on the surface that you get, small t, so this forms the basis of measurement actually. Okay, so maintaining the free load, an additional major load is added to reach the total required test load, and this test load defines the choice of the Rockwell scales actually. So whatever is the value of the major load that we apply, based on that, and we can define scales of measurement which we call as the Rockwell scale A, B, C, and there are like 62 scales actually based on the machine we are using. So initially you can see the functions of whatever are the loads that we are applying. So we have minor load or the preload that helps us create the reference line, and the value is always kept to be fixed at 10 kgf. Major load, it actually creates the impression or the depth of penetration actually, and its value will form the basis, not its value, the combination of the major load as well as the indenter type. So this combination actually that will define the choice of the Rockwell scale that we will be using for measuring the Rockwell hardness number. And dwell time I had already discussed. So allowing for the dwell time, we always allow for certain amount of the elastic recovery. So you can see that there are three positions actually. So this one is the indenter. Initially we are applying the preload. Then the main load is applied, keeping the preload there. Then there is a permanent depth of indentation, and then the major load is actually removed, and it is again kept for a certain dwell time to allow for the elastic recovery. And the final depth of indentation, small t, is measured actually, and this small t forms the basis for calculation of the Rockwell hardness number. So the Rockwell hardness number RHN. So initially these are the steps actually which I had told initially. So the major load is released, and after holding for a certain dwell time, the depth of indentation is measured. And this depth of indentation is the difference between the baseline and the final depth measurement. So this small t is actually measured, and the depth and the indentation depth is converted into the Rockwell hardness number. So this is the scale. So these are the various scales that we use for Rockwell measurements actually. So you can see like there are many scales actually. So whenever I am using a say 60 kg of force, so this load is the major load actually. So the major load can be 60, 100, 150. So this is the combination. And indenter type you can go on varying actually. So based on the combination of the load and the indenter type, we are defining actually certain Rockwell scales. So this one is HRA. So HRA means Rockwell hardness A, Rockwell hardness B, Rockwell hardness C. There can be many scales. You can define many scales of Rockwell hardness. So whenever I say that I have measured the value RA, so whenever you are measuring it on A scale, actually we get the Rockwell hardness number as something say RA. So RA is something where you are actually applying a major load of 60 kgf, and the indenter you are using is actually 120 degree diamond spheroconical indenter. So this spheroconical indenter, this diamond spheroconical indenter, this total thing is also sometimes referred to as a Braille indenter. So sometimes you may also happen to see that it is mentioned as Braille indenter. So you have to understand that the tip is actually 120 degree, the indenter is made of diamond, and the shape is actually a spheroconical. And its use is also specified actually. So this entire chart you can find it on the like body of the hardness testing tester actually. So if you go to the lab and you see the hardness tester, so on its body actually this total table is fixed. So based on the material that you are testing, so if you are testing a material of say tungsten carbide, then you have to use the Rockwell A scale. So whenever you are using like aluminum, brass, and certain softer materials, you have to apply for the B scale. So what scale you are actually be using, that is actually specified on the manual or the catalog that comes with the machine manufacturer. So this is the hardness scale B actually. So in the hardness scale B, you have the major load to be 100 kgf, and the indenter will be 101 by 16 inch, 1 by 16 inch steel sphere. Then whenever you are using the Rockwell C scale, so the major load will be 150 kgf force, and the indenter will be again 120 degree diamond spheroconical indenter, which is the Braille indenter. So these are the definitions of the Rockwell scales actually. So this is the Rockwell A scale. So whenever I am measuring something using the Rockwell A scale, I have to keep the major load as 60 kg. The minor load is always fixed. It is always 10 kg whenever if you are using RA, RB, RC. Whatever is the scale you are using, the minor load is always fixed to be at 10 kg. It doesn't change. What changes? The major load changes and the indenter type changes. So for a Rockwell A scale, you are having the major load to be 60 kgf, and the indenter will be a 120 degree diamond spheroconical indenter, which is also referred to as the Braille indenter. Similarly, when you are measuring something on the Rockwell B scale, the major load will be 100 kg, and the indenter type will be 16 inch steel ball indenter. So this is the indenter type that we will be using when you are measuring the hardness based on a Rockwell B scale. Similarly, the Rockwell C scale. So whenever you are measuring the hardness on a Rockwell C scale, you have to keep the major load as at 150 kg, and the indenter will be again 120 degree diamond spheroconical indenter, which is known as the Braille indenter. So the setup is shown here actually. So these are the things actually. So in all the cases, we are actually measuring the depth of indentation on the surface of the specimen, and whatever is the combination of the load and the indenter type that we are using, that actually forms the basis for defining the Rockwell scale that you will be adopting. So what Rockwell scale that you adopt, that you will be adopting for a certain specimen actually. So that is actually specified on the machine surface actually, on the machine catalog actually. So the catalog that comes with the machine, they will be mentioning like for what material you are supposed to use which specimen, and all these things are mentioned on the catalog that comes with the machine. So on the machine body itself, it's fixed actually. You can see that there is a chart consisting of 16 or 32 scales actually. So some machines have 16 scales, some machines have 32 scales. So all the combination of the scales are mentioned on the body of the machine actually, body of the tester actually, hardness tester, Rockwell hardness tester. So these are the three basic scales that we generally use. One is RA, RB, and RC. ঠিক আছে? দেখো এইটুকু ক্লিয়ার আছে কিনা? Again, it's just a diagrammatic representation of whatever I have said. So you can see that initially F0 is the preload of the minor load. Then keeping the preload, F0 plus F1. F1 is the major load that is applied on the specimen surface. Then finally the F1 is again removed. So F0 is applied. So you can see that when it's applied, it forms the basic datum surface. ঠিক আছে? Then F0 plus F1 is applied. So it goes to the second line actually. So you can see that it has overshoot the second line actually. So you have to keep the certain amount of dwell time. So after keeping the dwell time, you remove the major load actually. So the specimen actually recovers the elastic part and it comes back to the second horizontal line. So that this one actually, this length, so this part, as you can see, like this depth actually is the depth that actually forms the basis for measuring the hardness actually, measuring the Rockwell hardness. So দেখো এখানে কিছু doubt থাকলে you can ask. So this is the basic for measurement of the Rockwell hardness. Hello.
Hello, sir.
হ্যাঁ বলো।
So, sir, after giving major load, we have to remove major load and then wait for some time.
Again, yeah, you have to remove the major load and then again you have to give some dwell time. See, when you applied the major load, so in this case you applied the major load, so this overshoot actually. So this is not the second horizontal line. There was a, so this so you can see that it has overshoot by a certain thickness actually. So that is why I have kept this picture. So it has overshoot by a certain depth actually. So once you remove the load, once you remove the major load actually, and then you allow for the dwell time, this part will recover. This part of the deformation will recover. So that part actually forms the elastic part. So always you have to apply for certain amount of the dwell time. So unless you apply keep certain amount of dwell time, the measurements won't be perfect actually. The measurements won't be reliable. Because the elastic part after some time it vanishes, so there is no point in measuring all the elastic deformation part itself. So it will recover by itself. So you have to, so whenever after applying the minor load, you apply for a dwell time. After applying F0 plus F1, wait for a dwell time. Then after removing F1, you wait for a dwell time. So that whatever elastic parts appear during this deformation, that recover by themselves. That is the concept actually. So এটা যেটা বললাম RA, RB and RC scale, তিনটে scales খুব important. So these are very important things actually. What is the minor load for all the tests actually, all the scales, what is the major load for different scales that we use, and what is the indenter type that we use for different scales actually. So this is a Braille indenter. Braille indenter is used for Rockwell A scale and C scale, and for the Rockwell B scale you have a 1/16 inch diameter steel spherical indenter. ঠিক আছে? So a indenter types are very important. What is the value of the major load? What is the value of the minor load? What is the purpose of applying the minor load? So minor load actually forms the datum surface, the initial datum surface, because in any case we cannot take the surface of the specimen as the datum surface, because there can be certain irregularities, there can be many things as I discussed. So what is the purposes of the minor load? And all these things, এই জিনিসগুলো একটু just important, এই জিনিসগুলো একটু বোঝার দরকার আছে যে why we are measuring, what we are measuring, and how we are measuring. So last part is the testing precautions. So testing precautions are খুবই important actually. So it might look very easy or very trivial, but actually testing precautions are very much important from the viewpoint of hardness measurements. Is applicable to both RHN as well as BHN. So whenever you are actually measuring so in order to get a reliable value of the Rockwell hardness number, the thickness of the test piece should be at least 10 times the depth of indentation. So actually whenever you are indenting surface, so if the specimen itself is not rigid enough, like if you consider that it's a very thin specimen actually, so what happens is when you are applying the load using the indenter, actually the specimen will actually start to bend, so the measurements won't be accurate or won't be reliable. So that is why whatever is the thickness of the test piece that you are measuring, so the thickness of the test piece should at least be 10 times the depth of indentation. So if this is the like thickness of the test piece actually, so whatever you are, whatever is the depth of indentation that you are doing, so that should be 1/10 of that one. So you cannot indent it up to say this one actually. Okay, the indenter cannot be like say 50% indentation on the surface and all. Okay. So the readings should be taken from a flat perpendicular surface. So you can understand that whenever you are, since you are measuring a depth actually, so always all the surfaces should be perpendicular actually. The load you are applying should be in entire perpendicularity with the top surface of the specimen, or with the axis of the specimen. So the axis of the specimen should be in perpendicularity with the direction of application of the load actually. So unless that is not the case, the deflection that you are getting, that won't be the T we are measuring, the depth of indentation that we are measuring, that won't be that won't be a vertical displacement. Okay? Because convex surfaces give lower reading. So if the surface that we are measuring is something of a convex surface, say like this, suppose I am testing it on a surface like this. It's not a plate, so I'm testing it on a like spherical surface and all. So you don't get the actual measurements actually. So that you will be getting lesser values of the deflections actually. So whenever you are measuring a like convex surface or a spherical surface, you have to apply a certain amount of correction factor. So a correction factor can be used if the hardness of a convex surface is to be measured. So if you are using this for measuring the hardness on a convex surface, so you have to apply some amount of some suitable correction factors based on the problem actually. Okay? The test axis should be within 2 degrees of perpendicularity to ensure precise loading, that I told actually. So the perpendicularity should be within 2 degree limit. There should be no deflection of the test sample. That is very important. The test sample must be held very rigidly, or the tester during the loading application from conditions such as dart under the test specimen or on the elevating screw. So the elevating screw you are using, and on the test surface that you are holding the specimen actually, there must not be any dart or irregularities and like all those things, all those imperfections on the surface. And the surface to be measured must be clean and free from dart, grease, or decarburation from the heat treatment. So if there are any carbon layers, or if there are any surface coatings, dart, grease, and all those things, they must be thoroughly cleaned. There should be a like test specimen preparation phase where the specimen must be thoroughly cleaned. And sheet metal are very thin actually. So if you have seen. You have gone to the sheet metal shop, or you have done sheet metal jobs and all, like aluminum foils, very very thin foils actually. So in those cases actually, these are very soft and cannot be tested using the Rockwell tests. Okay? So sheet metal, since they are very very thin metal, very thin in thickness actually, very thin thickness materials actually, like aluminum foils and all those things, so they cannot be tested using the Rockwell hardness testing method. So micro hardness test, সেটা আমি আর বলছি না, মানে যেখানে মাইক্রো লেভেল ইন্ডেন্টেশন এন্ড অল হয়, এইটা আমাদের সিলেবাসে নেই, বাট এটা জাস্ট তোমাদের একটু জেনে রাখার দরকার আছে যে কি ধরনের ইন্ডেন্টার, মানে মোস্টলি হোয়াট ইউ নিড টু নো ইজ হোয়াট ইজ দ্য টাইপ অফ দ্য ইন্ডেন্টার এন্ড হোয়াট ইজ দ্য ভ্যালু অফ দ্য লোড এন্ড ফর which material you will be using the thing. So এই তিনটে জিনিসই widely used হয়. So these three tests are most widely used. Brinell, Rockwell and Vickers. So এই তিনটের কনসেপ্টই আমি বেসিক বলে দিয়েছি. So what is the difference between a Brinell hardness test and a Rockwell hardness test? এটা একটা খুব ইম্পর্টেন্ট জিনিস, যে number one is in Brinell hardness you are measuring the diameter, and Rockwell hardness you are measuring the depth. Number two is Brinell hardness is applicable for harder materials and coarse grains, and Rockwell hardness is applicable for softer materials and finer grains. ঠিক আছে? So এই জিনিসগুলো একটু জাস্ট বুঝতে হবে, and what are the differences between the different hardness scales that you are using. So that is very important from the standpoint of understanding the hardness scales. So this is what is regarding the hardness testings. So testing procedure টা তোমাদের ভিডিওগ্রাফিতে আছে, আমি ওটা যেটা আমি what I told is আমি সেটা নেক্সট ডে আবার ডিসকাস করব, সেটা একদিন জাস্ট টোটালি ওইটাই ডিসকাস করব. সো তোমরা এটা দেখো, আর আজকে আমি একটু জাস্ট আই এম স্টার্টিং উইথ দ্য টেনসাইল টেস্টিং অলসো. সো যেটা থিওরি পার্টস গুলো আছে, আগে একটু থিওরি গুলো করে নি. সো থিওরি পার্টস গুলো যদি আমাদের কভার থাকে, আই হোপ যে সেখান থেকে ভিডিওগ্রাফিটা খুব একটা টাইম লাগবে না. ঠিক আছে, মানে জাস্ট ইট উইল টেক ভেরি শর্ট টাইম টু ডিসকাস অল দোজ থিংস. জাস্ট কিছু মেশিন স্পেসিফিক যদি ডিসকাশনস থাকে সেগুলো কি আমরা করে নিতে পারবো. আচ্ছা, কে একজন জিজ্ঞেস করেছিল রিগার্ডিং দ্য এ বি সি স্কেলস এন্ড অল দোজ, সো তার কি এটা ক্লিয়ার হয়েছে, অর এনি মোর ডাউট রিলেটেড টু দ্যাট ইজ দেয়ার?
স্যার ডুয়াল টাইমটা কি 30 সেকেন্ড না 50 সেকেন্ড?
এখানে দাঁড়াও, ডুয়াল টাইমটা বোধহয় 30 সেকেন্ড। দাঁড়াও, আমি এখানে ডুয়াল টাইমের ভ্যালুটা আমি লিখেছিলাম।
স্যার ওই ভিডিওগ্রাফিতে দেখলাম 50 সেকেন্ড, কিন্তু আপনি আগের দিন বলেছিলেন 30 সেকেন্ড।
কোথায় লিখেছি 50 সেকেন্ড?
30 সেকেন্ড বলেছিলেন আপনি, কিন্তু ওই ভিডিওটা দেখলাম সেখানে 50 সেকেন্ড বলেছিল।
হ্যাঁ হ্যাঁ, ঠিক আছে, ওটা তোমার অ্যাকচুয়ালি মেটেরিয়াল টু মেটেরিয়াল ভ্যারিও করতে পারে, ঠিক আছে। ওই 30 সেকেন্ড 50 সেকেন্ড ওরকম একটা টাইম ফ্রেম আমরা রেখে দিই, ঠিক আছে।
আচ্ছা স্যার, থ্যাংক ইউ।
ঠিক আছে, ওটা ওটা 30 সেকেন্ডও হতে পারে, 50 সেকেন্ডও হতে পারে। এটা মানে ডিপেন্ডিং অন দ্য মেটেরিয়াল, এটা আমরা মানে ওটার কনসেপ্টটা ওটাই যে আমাকে ইলাস্টিক রিকভারি অ্যালাউ করতে হবে, ঠিক আছে। তো এবার কিছু মেটেরিয়ালে ইলাস্টিক রিকভারি তাড়াতাড়ি হতে পারে, কিছু মেটেরিয়ালে একটু লেট হতে পারে, সেগুলোর অনেক কিছু ব্যাপার আছে। সো মানে মোর ইউ কিপ দ্য মোর ইজ বেটার, মানে 50 সেকেন্ড যদি হয় তো সেটা ইটস বেটার অ্যাকচুয়ালি।
ওকে স্যার, থ্যাংক ইউ।
আর কিছু মানে ভিডিওর সাথে তোমরা তো একবার দেখেছো, ইউ হ্যাভ গন থ্রু দ্য ভিডিও ওয়ান্স, সো আর কিছু তোমাদের এই রিলেটেড ডাউট হলো, লাইক হ্যালো হ্যালো,
হ্যাঁ স্যার।
কোনো ডাউট আছে এই রিলেটেড? ভিডিওগ্রাফিটা তো তোমরা একবার দেখেইছো, ইউ হ্যাভ গন থ্রু দ্য
না স্যার।
ভিডিওগ্রাফি ওয়ান্স, সো কোনো ডাউট আছে
নো স্যার।
অন্য কারোর? হুম, ঠিক আছে। সো তোমরা দেখতে থাকো, তোমরা একটু টেনসাইল টেস্টটাও দেখে নাও, আমি একদিনই দুটো নিয়ে বসবো আর কি। নেক্সট ডেটা টোটালি আমরা ভিডিওগ্রাফিটাই ডিসকাস করবো। আমাদের দুটো এক্সপেরিমেন্ট হয়েও গেল আজকে। আজকে দেখছি কিছুটা অনেকটাই টাইম বেঁচে আছে, সো আমরা একটু টেনসাইল টেস্টিংটা ডিফাইন করে নিই, মানে ডিসকাস করে নিই। সো টেনসাইল টেস্টিংটা ডিসকাস করে নিলে আমরা নেক্সট ডে টোটাল টাইমটাই আমরা ডিভোট করতে পারবো ওই ভিডিওগ্রাফিতে, আমরা টোটাল ডিভোট করতে পারবো, ঠিক আছে। ওই এক্সপেরিমেন্টস গুলো দেখবো, বেশি টাইম লাগবে না, ঠিক আছে, জাস্ট আমি স্টেপ ওয়াইজ বলে দেবো। আর থিওরিটা ক্লিয়ার থাকলে আই হোপ খুব একটা অসুবিধা হবে না জিনিসটা বুঝতে। সো এটা এবার আমরা যেটা ডিসকাস করব, সো লেটস স্টার্ট উইথ দ্য, দেখো হার্ডনেস এ কোনো কোয়েশ্চেন থাকলে একটু জিজ্ঞেস করতে পারো, এলস উইল বি স্টার্টিং উইথ দ্য ডিসকাশনস অন টেনসাইল টেস্টিং। দেখে নাও একটুখানি, জাস্ট তোমাদের কাছে তো আছে, একটু প্রেজেন্টেশনসটা একটু দেখে নাও। সো লেটস স্টার্ট উইথ টেনসাইল টেস্টিং, আই এম গিভিং ইউ 2 মিনিটস, ঠিক আছে। দেখো কোনো ডাউট আছে নাকি স্টার্ট করবো নেক্সটটা? হ্যালো, ঠিক আছে। সো লেটস ডিসকাস অ্যাবাউট দ্য ইউটিএম, সো টেনসাইল টেস্টিং অফ মাইল্ড স্টিল। সো এখানে আগে আমাদেরকে যেটা বুঝতে হবে, হোয়াট আর দ্য টাইপস অফ দ্য মেটেরিয়ালস দ্যাট আর দ্যাট ফর্ম দ্য, তোমরা একটু তো স্ট্রেংথ অফ মেটেরিয়ালস বোধহয় পড়েছো, ইউ হ্যাভ স্টাডিড স্ট্রেংথ অফ মেটেরিয়ালস, আই হোপ ইউ আর অ্যাওয়্যার অফ দ্য টার্মস লাইক হোয়াট ইজ ডাকটাইল মেটেরিয়াল এন্ড হোয়াট ইজ ব্রিটল মেটেরিয়াল। পড়েছো না কিছুটা? তোমাদের স্ট্রেংথ অফ মেটেরিয়ালস ছিল কি ফার্স্ট সেমে?
নো স্যার।
আচ্ছা আচ্ছা আচ্ছা, ঠিক আছে ঠিক আছে। So ductile material is something that can undergo a certain amount of the plastic deformation like mild steel. So mild steel ke jokhoni amra we do like metal working on mild steel, actually tomra you have gone to the like workshop, you have gone to the workshop and you have done many sort of operations, like you have I hope you have done forging or you have done fitting shop করেছো বা এগুলো করেছো actually. So in the fitting shop you have like কি বলবো, you have like worked on the specimens actually, ঠিক আছে। সো সেইখানে you have actually deformed the material and you have seen that the material was capable of undergoing certain amount of the plastic deformation. কিন্তু কিছু ধরনের মেটেরিয়াল আছে, so there are some types of materials, say glass and all those things which cannot undergo any amount of plastic deformation. So the elastic part in itself, so it can it is unable to deform. So whatever is the elastic part, once the elastic part ends, the material actually totally ruptures. But if you consider a mild steel specimen, or if you consider a rubber, so any like normal rubber, if you consider, you are stretching the rubber. So once you are stretching the rubber, you are removing the rubber, you are removing the load, so the rubber returns back to its original position, and you can see that there is no residual strain on the specimen of the rubber band. So now you go on increasing the load. So a time will come when you will see that there is a kink, actually, like a neck sort of thing, or a gradual deformation occurs on the specimen of the rubber. And as you go on increasing the load, a time will come that the rubber specimen actually ruptures at the point that the kink has started. Okay? So I hope you can understand that rubber is a specimen that has a certain amount of elastic deformation, and it is also capable of undergoing certain amount of the plastic deformation. So once it's the kink actually appeared on the rubber, actually still it was able to withstand actually. But once you go on increasing the load, the diameter actually goes on decreasing actually, and a time comes when the specimen actually ruptures. Okay? And so there are actually two types of material. One is known as a ductile material, other one is known as a brittle material. So ductile materials are able to undergo certain amount of elastic deformation, but brittle materials are unable to undergo any sort of plastic deformation. So so mild steel, that is an example of an excellent example of a brittle material. Example of a ductile material. And brittle material is, say, glass. Okay? So so we will be doing the tensile testing of a mild steel specimen. Okay. So we will be doing the tensile testing on a mild steel specimen. So any tensile testing actually, so tensile testing means we are applying a tensile load on this specimen. Okay? So these are the loads that we can apply on a specimen. So suppose I am having a specimen, say a cylindrical bar of mild steel. So say suppose this is a cylindrical bar of mild steel that I am having, and I am applying a tensile load on this specimen. Tensile load means this is the cross-sectional area. So I hope you can understand that this is the cross-sectional area. So on the cross-sectional area, I am applying a tensile load. I am applying a pull actually. So I am applying a tensile load on this specimen. So what will happen is the specimen will elongate. So if the initial length of the specimen, or what we call it as the gauge length, so if the gauge length of the specimen was L0 actually, so the specimen will try to elongate to a length of L0 plus delta L. So this phenomenon is known as tensile loading of a specimen. So whenever I am having a specimen, so generally whenever we are doing a tensile testing on the specimens are mostly cylindrical in shape actually. Okay? So what we do is at both the ends, we fix them to two jaws on a UTM machine or a universal testing machine, and then we pull the specimen using two equal and opposite loads. Like on the top part, you are applying a load of P, on the bottom part, you are applying the same load of capital P. So they must be equal actually. On the both the bottom part and the top part, they must be equal actually. So let's see what happens. So what we are doing is we are doing the tensile testing on a mild steel specimen. The shape of the specimen, or the structure of the specimen is sort of a cylindrical bar. So a UTM is a machine, so it's known as a universal testing machine. So why it's universal? So universal testing machine because many sort of experiments can be conducted on the universal testing machine. So if you see in the lab, actually three basic tests. So the first one is the tensile testing. Number two is compressive testing. Compressive testing is very useful for civil application test. So compressive testing kisher jonne korte pari? Suppose brick. So if you consider, you look at the wall of your house actually. So you see that there are bricks. So the bricks, every brick, if you consider, they don't undergo any tensile loading. They are actually always under compressive loading. So any specimen that during application is supposed to undergo compressive loading, so for those specimens we will be undergoing a compressive testing, and the specimens that are supposed to undergo tensile during their service application, for them we do a tensile testing. So mild steel generally we don't do a compressive testing. Why? Because generally mild steel is supposed to be because it's a ductile material, so it's supposed to elongate a certain part actually. So whenever you are loading it, there will be a certain amount of elongation it can withstand. Okay? But whenever you're considering materials like brick, concrete, and all those things, mostly civil materials like brick, concrete, aro ja ja ache ar ki. So on them you have to do some compressive test. So in a UTM machine you can do a tensile test as well. You can do a compressive test. In addition to that, you can do a 3-point bending test, 4-point bending test. You can do many other tests on the universal testing machine, like using some attachments, obviously, like even the hardness testing machines and hardness testing, torsion testing, many tests actually that you can conduct on the UTM. Using some attachments, of course, not the normal UTM actually. So on a normal UTM, 3 basic tests you can do. So number 1 is tensile test, number 2 is compressive test, and the third one is your 3-point bending test actually. So these experiments that you can do on the UTM machine. So that is why it is called a universal testing machine. Universal means there are many sort of experiments that can be done on this machine actually. So on a UTM machine, what happens is a controlled and measured amount of the force. Controlled and measured amount of the force is applied on the testing specimen. So whenever you are actually testing the specimen actually, so let's first discuss what happens on the specimen. তারপরে আমি এখানে আবার ব্যাক করে আসছি। So আমি এইখানে দেখো, so let me explain it here. So let me explain it here. So initially you can see that we are having a specimen. Actually, since I am looking at the front view, I am able to see a rectangle. So it's actually a cylindrical bar actually. So you are having a cylindrical bar of length say L0. So L0 is the gauge length of the specimen. Now what I am doing is on both sides of the specimen, I am applying equal and opposite forces of capital F using two jaws actually. So whenever you go to the UTM machine actually, so on the UTM machine you have an upper jaw, you have a lower jaw. So both the jaws actually apply equal amount of tensile forces on the top surface and the bottom surface of the specimen. Okay, what is the usefulness of applying the ki bolbo, applying the measured and controlled force? মানে এই যে দুটোই both are same F. So what is the usefulness? So if the top part the force is F and the bottom part the force is F plus delta F. So the lower part is actually getting more stressed. So the fracture will occur at the lower part. So that we don't want. What we want is we want that the entire specimen actually it's a homogeneous specimen. So what I am doing is I am loading it equally on the top side and I am loading it equally on the bottom side. So what will happen is the specimen will elongate. So initially there will be certain amount of elastic deformation. So you can see that in the second example, this one, you can see that the length has increased. So initial length was L0. So the length has increased to say L1 in this case. You go on increasing the load. So it's a gradually applied load. You are applying the load very gradually, very, very slowly. So the length actually increases to L2. So up to this L2 part actually, so the specimen increases to a length of L2 minus L0. So if you want to calculate delta L, so delta L was initially L1 minus L0, and in the next case the elongation was L2 minus L0. So you can see that whenever you are deforming the material, actually the material has no plastic part developed on it. There has been no deformation on this specimen. So if I remove the load at this point actually, so on the second part of length L2, if I remove the force F actually, the specimen will follow its original path and it will return back to its original position of original length of L0. So this is actually so it can undergo certain amount of elastic deformation. Now if you go on increasing the load after a certain limit, what will happen is the specimen will start to develop a neck on the specimen actually. So suppose this is the specimen actually. So this is a cylindrical specimen. So এখানে actually আঁকাটাই খুব মুশকিল actually. So this is a specimen. What I am doing is I am applying certain amount of load on the specimen. So what will happen is, so initially it was something like this. So after I load it, after a certain limit, what will happen is there will be a necking on the specimen. Necking means there is a reduction in diameter of the specimen. The specimen is elongating. So in order to keep the volume actually, so this part, so this part you can see that there is a reduction in the diameter of this specimen. So neck, if I say neck, what is neck? In our body, neck is having a sudden reduction in the diameter actually. So this part is known as a necking actually. Why? There is a sudden reduction in the diameter. Because you are going on increasing the length, but the volume has to be kept constant. So that is why at certain point actually, there will be start of a permanent deformation. So this permanent deformation, whenever it starts creeping in the material or it starts when it starts in the material, you are having a certain reduction in diameter on the specimen actually. So this part you can see that there is a necking being started on the specimen, and if you go on increasing the load, there will be certain cavities being formed in the material. So you can see that there are very small like bubble sort of things being formed in the material actually. And again, if you go on increasing the load, a time will come when these bubbles will actually coalesce among themselves. So this bubble will combine with this one, this one, and this one. So there will be coalescing of the bubbles, and a time will come when the specimen will actually fracture. These bubbles will combine, and then there, since you haven't studied like strength of materials actually, so ekhane the fracture type that is known as a cup and cone fracture. So when you study like whenever you go and study like strength of materials, you will see that or any like ductile material, they undergo a cup and cone type of fracture. So you can see that this is a cone. So this one is a cone. So you can see that there is a cone type of shape, and bottom you are having a cup type of fracture. So this one. So you can see that this is the necking. So you are having a specimen. You are pulling the specimen. You are applying a tensile load on the specimen on both sides. So what happens is, after a certain time or after application of a certain load, initially the material will be in the elastic zone, and then after a certain time actually, what will happen is the specimen will start to neck. There will be a gradual reduction in the diameter of the specimen, and a time will come when the specimen will actually break, with this one being being the cup side. So you can see that this is the cup space. This is the cup. Okay, this is the cup, and this is the cone actually. This is the cone, and this is the cup. So this is known as the cup and cone fracture of the specimen. So generally এই যে অ্যাঙ্গেলটা হয় when you do like strength of materials and all, so সেইখানে তোমরা দেখবে, so it actually fractures at angles of 45 degree. এই যে 45 এই যে প্লেনস গুলো হচ্ছে না, এগুলোকে লিডার লাইন্স বলা হয়. So এই লিডার লাইন্স, so they fracture along these leader lines which are inclined at 45 degree with the axis of the specimen. ঠিক আছে, তাহলে এইটা টোটালি এইটা 45 ডিগ্রি হবে সব দিকে। এটা 45 মানে কি, এভরি সাইড ইট ইজ অ্যাকচুয়ালি 45 ডিগ্রি। ঠিক আছে, এই যে ফ্র্যাকচারটা হচ্ছে, সো দিস ফ্র্যাকচার অলওয়েজ অকার্স at 45 ডিগ্রি ইন কেস অফ ডাকটাইল মেটেরিয়াল। সো এই যে ফ্র্যাকচারটা হয়, দিস ফ্র্যাকচার উই কল ইট অ্যাজ এ কাপ এন্ড কোন ফ্র্যাকচার। আচ্ছা, এবার আমরা আবার ব্যাক করে চলে যাচ্ছি যেখানে আমরা ছিলাম। So UTM আমরা generally যেটা করি, in a UTM the force has to be applied in a controlled and a measured fashion. Why controlled and a measured fashion? তুমি যদি control না করো, if you don't control actually, so what happens is, ধরো এই স্পেসিমেনটা, suppose in this specimen দেখো the fracture actually occurs just at the middle of the specimen. তো তোমার যদি actually loadingটা যদি uniform থাকে, so if the loading is uniform, the loading is gradual, number one, and you are applying the load in a very like gradual fashion, and the load is equal at the top and the bottom actually. ঠিক আছে, both are F actually. সেটা যদি না হতো, আমার যদি at the top I am applying F and at the bottom I am applying F plus delta F, so what will be happening is the fracture যেটা হবে, so the fracture will be occurring not at the center actually, at a distance away from the center. বা এমন হতে পারে, সাপোজ দেয়ার আর সার্টেন হার্ড স্পট, সাপোজ দেয়ার আর সার্টেন কার্বাইডস, অর দেয়ার ইজ মানে ধরো সাম ইম্পিউরিটিজ আছে বা এয়ার বাবলস আছে বা কিছু ডিফেক্টস ইন দিস স্পেসিমেন আছে, সো ইন দ্যাট কেস the fracture won't be at the middle of the specimen, it might occur at the sides or ends actually. ঠিক আছে, সো এইটা একটা খুব ইম্পর্টেন্ট জিনিস। সো দিস ইজ আ ভেরি ইম্পর্টেন্ট থিং। সো whenever you are doing a UTM testing actually, the specimen must be very much uniform and should be free from all sort of defects and all those things. So it is specimen that we use so generally in the labs and all, when we do the experiment, many time comes when the specimen actually fractures just at the bottom or just at the top, মানে near to the jaws, the part that are fixed to the jaws, মানে এই যে পার্টটাতে actually jaw fixed আছে, so এই পার্টটা, this part is fitted to a jaw, the upper jaw, and this part is fitted to a jaw, the lower jaw actually. So এই যে jaw so the parts that are closer to the jaw, these parts are more prone to fracture. Because ঠিক আছে, why? Because you may apply the load very like the load may be sudden, so the load has to be applied very gradually and very controlled fashion. So হঠাৎ যদি, if it's a sudden load or say an impact load, the specimen will fracture near the jaws itself, or if there are impurities at any point, say here or here, the specimen will fracture at those points. So there are two important things. One is regarding the load. The load has to be very gradual, and the load has to be applied in a controlled and measured fashion. And regarding the specimen has to be well prepared with no defects and no impurities in the specimen. So the amount of the extension is measured. So whatever is the extension in the specimen, that is measured and graphed. ঠিক আছে, so এখানে measurements কি আছে? So you are applying a force and you are measuring the deflection in the specimen. ঠিক আছে, so this is the force that you are applying. So এই direction এ ধরো, So on this direction you are having the force, the tensile force you are applying, and on this direction you are having the delta, the deflection that is occurring in the specimen. You can do as other thing also. What you can do is, you know, the cross section of this specimen. What you do is you divide it by the cross sectional area of this specimen, capital A, and you divide this delta by the gauge length of this specimen. Say the length actually changes. So what I do is I divide it by the original length, say L0, and I divide it by the original area, say A0. So in that case, I am getting F by A0 is the stress, and delta by L0 is actually the strain. So that diagram is also known as the load deflection, is known as the stress strain diagram. So sigma by sigma epsilon. So both have the same nature actually. Okay? So because A0 and L0 they are constant, so if either you plot the force deflection curve, Fx curve, so either you draw the force deflection diagram, F delta curve, or you draw the stress strain curve, both will be having the same nature actually. So আমাদের outcome টা কি? So what is the final outcome of a UTM machine? So final outcome of a UTM machine is we measure the force deflection diagram or stress strain diagram. So stress strain diagram is the final outcome of a UTM test. কি হয় সেটা? এটা আমরা যাবো। আচ্ছা, UTM মেশিনে আমরা কি কি মেজার করতে পারি? We measure the stress, strain, elasticity, tensile strength, ductility, shear strength. All these things can be calculated theoretically or graphically from the tensile test data. So whatever is the tensile test data that we are getting. So what is the tensile test data? So tensile test data is the FX diagram or the force deflection diagram or the stress strain diagram that we get from the tensile test data. We have to plot the stress strain. We have to plot the force deflection or stress strain actually. So that data, from that data we can derive the stress, strain, elasticity, tensile strength, and all those things we can derive from that one. আচ্ছা, the test specimen is generally round or flat in nature, যেটা আমি একটু আগে বলছিলাম, which I was discussing, that generally the test specimen that we take, they are either they are cylindrical in shape or they may be flat in shape. The cross section might be circular or the cross section might be your কি বলবো, square. ঠিক আছে? আচ্ছা, ductile materials, যেটা আমি একটু আগে which I discussed, the ductile materials mostly mild steel, they undergo a cup and cone type of fracture. এক সেকেন্ড হোল্ড করো। ঠিক আছে? হ্যালো, হ্যাঁ, ওকে। সো এত অবধি আমরা ডিসকাস করলাম। নেক্সট আমরা যেটা ডিসকাস করব সেটা হচ্ছে নিড ফর মেটেরিয়াল টেস্টিং। আচ্ছা, এই যে এতগুলো যে মেটেরিয়াল টেস্টিং আমরা করছি, অল আর মেটেরিয়াল টেস্টিং অ্যাকচুয়ালি, আইদার ইউ ডু দ্য টেনসাইল টেস্ট or you do the compressive test, you do the hardness testing and all those things that you do. What is the need for all those things? So ensure the quality of the engineering material. So দেখো, whenever you are going for a service application, you have to ensure that the material that you are using are actually are up to certain engineering standards actually. So in order to identify the quality of the engineering materials actually that you are using for a specific application, you have to apply the material testing. The test properties are very vital parameters. Okay? Based on the application, you have to choose the material actually. So for that, you have to derive the material properties of the material to assess or prevent the failure in the field applications. So during the field applications, you have to assure that the specimen doesn't fail. And material selection based on engineering data. So whatever is the based on engineering data. So we have to do some material selection actually. So for which application we have to use which material. So suppose for an say aerospace application, you have to use a different sort of material. So তার জন্য you will be having to তার জন্য there will be a set of data. And for a different thing, say suppose কি বলবো, like some home application you are using something, so for that you will be having a different set of materials. তার জন্য ধরো আমার অ্যালুমিনিয়াম স্টিল ইউজ করছি। ইন এরোস্পেস উই আর ইউজিং লাইক কি বলবো, এরোস্পেসে ধরো তোমার FGM বা composite materials, এই ধরনের materials use করছি। So for the application that you are using, so you have to go for certain material selection. So that material selection, so in order to arrive at the material selection, you have to conduct these engineering tests. ঠিক আছে? So আচ্ছা, এবার টেস্টিং যেটা হয়, so testing are of two types. Now one is known as a destructive testing and another one is known as a non-destructive testing. So what is the destructive testing? Destructive testing মানে হচ্ছে suppose tensile testing. এই যে tensile testing you have seen that we are loading the specimen and the specimen at the final actually, so we are plotting the load deflection diagram and all, and at the end stage actually the specimen actually ruptures or breaks. So do you feel that the specimen after its testing is applicable for the engineering application? Is suitable for the engineering application? No. Right, so actually the specimen is ruptured. It's a destructive case, so the specimen has been destroyed. So it is not available for the future application actually. Right, so hello.
Yes, sir.
So it's a destructive test. So this tensile testing, it's a sort of a destructive test. So what we do is we take a specimen. তো এখানে কি হয় repeatability হতে পারে. Suppose I take 100 specimens and I test only one specimen. So that the properties that I get from that one specimen, say Young's modulus or anything like shear modulus, whatever you get for that specimen, all the other 100 specimens that will be having their properties exactly similar, if not exactly similar, within a certain tolerance limit of that specimen. So if I can test only one specimen, I can guarantee that all the specimens in that lot or in that batch, they conform to the same standards actually. So that is certain, that is known as tolerance feeds or standardization of the specimens. এগুলো আবার আছে. These are different things. But whenever you are going for a destructive test, you have to keep in mind that the specimen you are testing actually. So you are testing one specimen from the batch, and all the specimens that are in the batch, that must conform to that. That must be having the close agreement with the properties of the one specimen being tested. বোঝা যাচ্ছে তো? মানে I cannot test each and every specimen. Because it is a destructive test, I cannot test each and every specimen that is coming in the batch. I have to test one specimen. But the manufacturing process that I am using, that should be having so much repeatability that it can repeat the same properties in the specimen that it goes on manufacturing. বুঝতে পেরেছো? আচ্ছা, সো যেটা আচ্ছা মেটেরিয়াল প্রপার্টিজ আমরা কি কি পেতে পারি টেনসাইল টেস্টিং থেকে? আমরা ইয়াংস মডুলাস পাই বা মডুলাস অফ ইলাস্টিসিটি, সেটা কি আমরা আসবো, উই উইল বি কামিং টু দ্যাট ওয়ান. নেক্সট ইজ ডাক্টিলিটি, ইলাস্টিসিটি, স্টিফনেস, আচ্ছা মডুলাস অফ টাফনেস, মডুলাস অফ ইলাস্টিসিটি, অল দোজ থিংস আমরা মেজার করতে পারি. আচ্ছা, what is a tensile tester? Is a tensile testing machine বা tensile tester that we discussed. So it's a machine which applies the tensile force to the specimen and that measures that force and also the elongation. So in a tensile test, we have the arrangement so that a controlled and measured tensile force can be applied on the specimen, and the specimen also has arrangement so that the force and the elongations can be measured. Okay? So after applying the force actually, you go on increasing the load, and in each step you measure the force and you measure the deflection actually. So in order to measure the deflection, you will be having some extensometers fitted on the specimen. Okay? So since the extensometer is fitted on the specimen itself, so specimen how long the specimen elongate, the extensometer will also elongate by that thing actually. বুঝতে পেরেছো? মানে এক্সটেন্সোমিটার it has got a different principle actually, but extensometer কাজ হচ্ছে it is fitted to the specimen and it measures the deflection that occurs in the specimen. So finally we are measuring the force and the deflection on the specimen, and also in most of the UTM machines actually you have a plotter actually. So there is a plotter, there is a pen and paper arrangement where we can directly get the F delta curve actually. And in modern machines that are coming, they have the a machine interface. They have a computer interface. So whenever you are loading a specimen, so that force and deflection, they are directly measured, and then the computer actually, so the data passes on to the computer, and in the computer itself you can measure the load deflection diagram. So you can get the load deflection diagram directly on your computer itself. The computer is interfaced with the UTM machine itself. Achha, so the load you are applying, so this tensile force that you are applying, so that is basically applied using a hydraulic cylinder actually. So there is a hydraulic setup actually. So using that hydraulic force actually, so unless it's a hydraulic force or that thing actually, so you cannot apply a very controlled force actually. So that is why we have to keep a hydraulic cylinder or a hydraulic unit in order to apply the tensile force on this specimen. ঠিক আছে? এখানে যেহেতু একটু since we require a heavier amount of load, that is why it's a hydraulic arrangement. যদি lighter arrangement হতো, মানে for a lighter arrangement you can use a pneumatic cylinder also. Pneumatic মানে জানো তো, hydraulic and pneumatic এগুলো নাম শুনেছো? Hydraulic cylinder মানে it is operated by a fluid pressure, and pneumatic মানে it is operated by air pressure. So there is a fluid in a closed vessel, and there is a piston fitted. So if you go on, so that actually applies the pressure. So that is something known as a hydraulic cylinder. and if it works on using air pressure, we call it as a pneumatic cylinder. ঠিক আছে? So the force যেটা apply করা হচ্ছে, the force we are applying, that we are applying using a hydraulic arrangement actually. একটা arrangement করা আছে, there is a hydraulic cylinder based on which the force is being applied. Acha. So the applied force is determined by the system pressure, which is accurately measured. Acha. So this is a hydraulic UTM actually. তোমরা এটা আমি জানি না তোমরা UTM এর I don't know if you have seen the UTM testing, like tensile testing and all. So this is the arrangement that we have. আমাদের সেটআপটা যেটা আছে, so you can see that there are two jaws actually. ঠিক আছে? So এইখানে দেখো there is one jaw. This is the upper jaw and this is the lower jaw actually. So এই পার্টে actually the specimen will be fixed. এই পার্টে actually the specimen will be fixed. এইখানে আমাকে একটু ওই ভিডিওগ্রাফিতে যেতেই হবে। So next day আমি এটা আরেকটু ডিটেল করব, মানে ফ্রম দি ভিডিওগ্রাফি আমরা এক্সপ্লেন করব। আজকে আমি জাস্ট বেসিকটা বলে রাখছি, ঠিক আছে? আচ্ছা, যেটা আমি বললাম যে UTM operation either it can be mechanical or hydraulic. Mechanical মানে it can be operated using a motor or a gear and all those things, and hydraulic মানে it's being operated using a fluid pressure. Either there is a single acting or a double acting piston to move the crosshead upward or downward to apply the load actually. আচ্ছা, এইটা হচ্ছে যে কাপ এন্ড কোন ফ্র্যাকচারটা which I discussed, যে the specimen is gripped in two jaws. So you are having two jaws in the UTM machine actually. So the specimen is fitted between the jaws and the load is applied on the specimen actually. So one is actually a fixed jaw and another one is a movable jaw actually. দুটো জয় মুভ করছে না। One is a fixed jaw, other one is a movable jaw. So whenever the load is applied, so there is a deformation on the specimen. So in order to measure the deflection on the specimen, as I had discussed that, we use two extensometers. Okay? So there is a left extensometer, there is a right extensometer. So on this specimen, on the left side, we are fixing an extensometer. On the right side, we are fixing a extensometer. So we are getting some data or deflection or extension from the extensometers. So what we do is, whatever you are getting from the left extensometer, whatever you are getting from the right extensometer, you take the average of the two values and then you get the actual deformation in the specimen, delta jeta. So here I was just discussing, so up to this I had discussed that whenever you go on increasing the load, actually a time will come when the specimen will actually neck. And if you go on increasing the load, a time will come when visible bubbles will appear actually, or visible deformations will occur in the specimen. Then the bubbles will coalesce among themselves, and a time will come when the specimen will actually fracture. Okay, the specimen totally it will fracture using a cup and cone fracture sort of thing. Okay. So finally what we do is we measure the final length. এই যে specimen দুটো আছে, specimen দুটোকে জোড়া দিয়ে we measure the final length LF. So সেইখান থেকে we can calculate the মানে তোমার epsilonটা we can calculate LF minus L0 divided by L0. So from there we can calculate the strain in the specimen. আচ্ছা, এইটা হচ্ছে তোমার এই flat test piece and round test piece এর ব্যাপারটা যেটা. So we have to take one gauge length actually. So what is the gauge length? Gauge length is the length on which the actual measurement is being done. আমরা the total length we don't take. So this total length we don't take into account. Why? Because these two parts are for fitting in the jaws of the machine. So এই দুটো part যেটা আছে, this part actually goes inside the jaws. এই পার্টটা actually jaw এর inside এ চলে যাচ্ছে. So that is why this part actually, so on this gauge length part all the calculations are done. ঠিক আছে? And the cross section of the specimens, either they can be round or a cylindrical specimen, or they can be a flat test piece. আমি test piece গুলো দেখিয়ে দেবো next দিন. So load deflection diagram. So at each step we measure the load and we measure the deflection, or either we can do that, or as I discussed, either we can divide the load by the cross sectional area, original cross sectional area, or we can divide the deflection by the original length, so that we get the stress strain diagram. So this indication, so the plot that we get, that is known as a stress strain diagram. So each material, so depending on the type of the material, we get a unique stress strain diagram of the specimen. So this is a typical stress strain diagram for a ductile material, say suppose mild steel that we are testing in the lab actually. So initially you can see that, so on this side we have plotted the force, on this side we have plotted the extension. So on this side you are having F, and on this side you are having the deflection delta. ঠিক আছে? সেটা তুমি আসছি দেখে নি আর কি বলার বাকি ছিল, দিয়ে আমি কার্ভটা একটু এক্সপ্লেন করব। আচ্ছা, নেকিং রাপচার কম্পারেটিভ, আচ্ছা ব্রিটল, ঠিক আছে। দিস পার্ট এইটা আমরা নেক্সট ডে ডিসকাস করব, এই জায়গাটা আমি একটু বলে নিচ্ছি। সো নাও ইউ ক্যান সি Acha. So this is a stress strain diagram of a specimen, or a load deflection diagram of the specimen, as I discussed that whatever is the nature of the force deflection diagram, the same nature of curve you will be getting if you plot the stress strain diagram based on the initial cross-sectional area and the initial length actually. So since the initial cross-sectional area A0 and the initial length or the gauge length L0 was fixed actually, so the nature of the stress strain diagram and the nature of the load deflection diagram will be the same. So initially you can see that there are some points on the graph actually. So initially there is something called a limit of proportionality or proportional limit. So what is this proportional limit? So আমি গ্রাফটাকে পাশে পাশে আবার আঁকতে আঁকতে যাচ্ছি. I am just drawing the graph as I feel suitable. It is drawn here also. আমি just একটু explain করতে করতেই যাচ্ছি. Let me just keep on explaining the thing also. ঠিক আছে? So initially দেখো, so initially there is a elastic zone. তার মানে whenever you are loading the specimen actually, so as you see that this is the force direction, so this is F and this is delta. So you go on increasing the load, there is a deflection in the specimen. So এই যে জোনটা আছে, so up to this elastic limit, so এই যে initial যে পয়েন্টটা, I am calling it as the point A. So point A refers to the your proportional limit. So what is proportional limit? So proportional limit means the F is proportional to delta, the force that varies directly as the deflection delta. So this is known as the proportional limit. Proportional limit মানে the force is proportional to delta. So whatever is the force you are applying, so F is equal to Kx. When it's sort of a like linear spring actually, F is equal to K delta. So if I remove the load, suppose at this point, I come and then I remove the load. ঠিক আছে? So if I remove the load, what will happen is the specimen will follow the original path and it will return back to the zero extension point without, so that there is no no visible extension or no visible plastic deformation on the specimen, or you cannot even understand that the specimen was ever loaded. So whenever the specimen is within the elastic limit or the proportional limit, you can never understand that the material was ever loaded, because once you remove the load actually the material follows the original path and it when all the extension that was there inside the specimen, so the extension or the elongation was actually delta elastic. So all the elastic deformation actually vanishes, so that once you remove the load there is no visible deformation or no strains being developed inside the material. ঠিক আছে? So এই করতে করতে you reach one point capital A and there is a distinct point capital B away from it. ঠিক আছে? So there is a distinct point away from it. So this is the point B. So what is the point? What is the difference between these 2 points? So the point A is known as the proportional limit, and the point B is known as the elastic limit. So what is the difference between the limit of elastic limit and the proportional limit? So at the point A, the proportionality ends actually. So once you cross the point A and so within the point A to B, আন্ডুও করা যায় না, ঠিক আছে? সো এইটা একটু বি হবে, হ্যাঁ, আই হোপ ইটস ভিজিবল। এটা অ্যাকচুয়ালি বি, বুঝতে পারছো তো? সো ফ্রম দি পয়েন্ট 0 to A, হ্যালো, সো ফর দি পোর্শন 0 to A, মানে 0 to A যে পোর্শন আছে সেখানে ফোর্স ইজ প্রপোর্শনাল টু ডেল্টা, মানে F ইজ ইকুয়াল টু Kx, ঠিক আছে? বাট ফর দি পোর্শন A to B, মানে আমি যদি A to B কনসিডার করি, মানে once I had crossed the proportionality limit or the proportional limit, যেই proportional limit cross হয়ে গেছে, this F মানে proportionality has actually ended, ঠিক আছে? মানে এখানে তোমার F is proportional to delta plus the material is elastic, ঠিক আছে? But once you cross the point A actually, the F proportional to delta thing vanishes. F is not proportional to delta, but the material is still elastic. So for the part OA, the material is elastic as well as it follows the force is proportional to the deflection. But once you cross the point capital A or the proportional limit, the limit of proportionality actually ends. F is not at all proportional to delta, but still the material is elastic. So what happens is A for A, any point between A and B, you remove the load, the material is elastic. The material will return back to its original position O, and there will be no visible strain in the material, no visible plastic deformation in the material, but the force is not at all proportional to the deflection. ঠিক আছে? For the portion OA, force is proportional to deflection and it is elastic. But for the portion AB, force is not at all proportional to deflection, but still the material is elastic. The elasticity thing is there up to the point B. but force is not proportional to deflection for the part AB. But for the part OA, the material is elastic as well as the force is proportional to deflection. ঠিক আছে, it's a very মানে কি বলবো মানে খুব একটা distinct নয়, মানে A and B they are very closely lying, মানে most of the experiments you won't be able to like differentiate the points A and B itself. And for most of the engineering materials, the differentiating such points are very difficult actually. So in the laboratory experiments that we do, এই যে points গুলোকে identify করা, it's a very difficult thing. মানে A আর B এর মধ্যে the কি বলবো the spacing between the points A and B is very small that identifying them is very difficult. But still you can identify that for the point A up to the point A, force is proportional to deflection, and up to the point A to B, force is not at all proportional to deflection. But up to from O to B, the material remains elastic. Elastic means there is no plasticity in the material. Once you remove the load, actually the material still returns back to its original position, and there is no visible strain in the material, no visible deformation in the material, so that you can ever understand the material was ever loaded. Material that loaded হয়েছিল still you cannot understand. ঠিক আছে? So এই যে force is proportional to delta আছে, so আমরা কি করি এই force proportional to delta টাকে আমরা এটাকে লিখি. So আমরা যদি এটাকে লিখতে পারি যে আমরা যদি এটাকে if we consider it to be the stress strain diagram, ঠিক আছে, মানে initially from the experiments we get the force deflection diagram, and from there we draw the stress strain diagram by dividing the force with A0 and by dividing delta with L0. So from the stress strain diagram we can say that for the part OA or for the part AB, মানে up to the elastic limit আমরা এটা বলি, which we say the Hooke's law actually states that up to the elastic limit this stress is actually proportional to strain. So this stress is actually proportional to strain. So এই যে stress is proportional to strain, so stress by strain must be a stress strain করে দিচ্ছি. So stress is proportional to strain. So stress by strain আমি যদি করি, so if I do stress by strain, so that is the constant actually. So this constant we call it as the Young's modulus or the modulus of elasticity. So this stress by strain within the elastic limit is known as the Young's modulus or the modulus of elasticity, such that sigma is equal to E epsilon. So this E is known as the Young's modulus of the material. So for mild steel, the value of the Young's modulus is something like 210 gigapascal. ঠিক আছে? So sigma is equal to E epsilon. So that stress is proportional to strain within the elastic limit of the specimen. So এই যে formula, this thing is actually known as Hooke's law. So Hooke's law states that within the elastic limit, stress is proportional to strain, and the constant of proportionality is known as Young's modulus of the specimen. ঠিক আছে? So এইবার আমরা যে now once we cross the point B, actually এই B পয়েন্টটাকে আমরা যে ক্রস করে গেলাম, so আমরা একটা পয়েন্টে আসি which is known as the upper yield point. So yield point মানে the material has started to deform. So whenever there is a plastic deformation in the specimen, we call it as a yield point. So there is a upper yield point, then there is a lower yield point. Specimen take to certain drop করছে, so there is a lower yield point of the specimen. Then actually the material actually strain hardens. ঠিক আছে? Strain harden হয়ে there is a sudden reduction in the force actually. And then here you are having an ultimate stress, and after that there is a breaking stress. এইখানে একটা পয়েন্ট আছে which is known as the breaking stress. So এইটা হলো C point, এইটা হলো D point, this one is the E point, and this one is known as the F. F is the breaking point. ঠিক আছে? তোমরা একটু লিখে নাও এটা এখানে অ্যাকচুয়ালি লেখা নেই, সো আমি দেখছি নেক্সট ডে যদি আরেকটা কোনো, আচ্ছা এটা বোধহয় লেখা আছে সাইড করে, অ্যাকচুয়ালি লেখা আছে খুব ক্লিয়ারলি, যদিও লেখা নেই। So এইটা দেখো, this one is the upper yield point. So this one you can see that this one is known as the upper yield point of this specimen. So এই যে C pointটা, so C point is known as the upper yield point of this specimen. So once you have crossed the point B, এই যে point B টা তোমরা যেই ক্রস করে চলে গেছো, once you had crossed the point B, the elasticity thing actually ends. So the material is not at all elastic. So এই পার্টটুকুর জন্য the material is elastic. This is the elastic part in the specimen, and away from B the plastic part starts. So B থেকে once you move from the point B, you go on applying the load, the material actually moves to the plastic zone, so that you are having an upper yield point. So upper yield point মানে যে নেকিং টা actually start হচ্ছে তোমার yield point থেকে start হচ্ছে. Once the specimen has started once you move from the point B, actually the necking phenomenon actually starts. So there is an upper yield point. Yield point মানে যেখান থেকে actually the visible deformation or visible necking actually appears. ঠিক আছে? You can see that the necking has started in the specimen. So এইখানে দেখো, up to this you can see that force is proportional to delta, but after this you can see that the specimen is actually flat. ঠিক আছে, এইখানে দেখো, so if you see যে দেখো ফোর্সটা মানে এইখানে বা এইভাবে যদি বোঝাই, so এইখানে দেখো the force is this, এইখানে হচ্ছে up to this one, suppose you are applying a force, ঠিক আছে, after that you see the force hasn't increased too much. So you can see that the force hasn't increased too much. So this is delta F. So in the plastic zone, you are not at all applying any force. But still you can see that there is a huge deformation in the specimen. So that is something that defines plasticity. এটা একদমই ঠিক আছে, আমি নেক্সট ডে এটা পারলে একটু এতেও একটু এক্সপ্লেন করে দেবো, ঠিক আছে, ওই পেন ট্যাবে একটুখানি বলে দেবো, খুব মুশকিল বলা। ঠিক আছে, ছেড়ে দাও। So you can see so see, up to this you are applying a force and there is an extension, there is a proportionate extension. But after this, this is the elastic limit. Once the elastic limit you cross, you can see that the curve is something like this at a lower yield point, and then there is a ultimate load and there is a breaking load. So you can see that the force hasn't increased too much. So you can see that the force, you haven't increased the force beyond the elastic limit too much, but you are getting a higher amount of deformation in the specimen, so that you don't apply too much load, but the material has become plastic. That means that when the material becomes plastic, even a small amount of force actually causes a very large amount of deformation in the specimen. So that actually defines plasticity. The material is not at all elastic. Once you apply a very small amount of load, actually causes a very, very high amount of deformation in the specimen. That is why আমরা forging করি। তোমরা forging করেছো তো, you have done forging lab. Hello? So forging, you can see that the material was actually plastic zone. তোমরা এত amount of, you can give a high amount of deformation on this specimen at a high temperature. Why? Because the specimen at the high temperature is actually in the plastic zone. So in a plastic zone, even by applying a very low amount of force, you can cause a very high amount of deformation. So all the metal working operations যেটা তোমরা করেছো, they were actually plastic deformation in the specimen. Why plastic? Because you can see what the deformation you are causing on the specimen. Like forging, you are reducing the diameter, or you are কি বলবো, drawing করছো বা upsetting করছো, যাই করছো, whatever you are doing actually, so you are actually plastically deforming the specimen. ঠিক আছে, so in the plastic zone actually you are applying a very small load, but you are causing a very high deformation on the specimen. So that defines actually plasticity. So এই যে plastic zone টা আছে, so here actually you can see that there is a upper yield point, there is a lower yield point. Then E point is known as the তোমার কি বললাম, the ultimate strength of the material, and finally the point B, actually you can see that at the point B there is the cup and cone fracture of the specimen. ঠিক আছে, so এইখানে দেখো, এটা হচ্ছে different type of materials, they will be having a different stress strain diagrams for them. কোনো material এর জন্য দেখো, for different materials you will be having different, but the nature of the curve actually remains the same. The important thing is the nature of the curve. So initially you are having an elastic zone where you can see that the stress is proportional to strain, and once you cross the elastic zone, you can see that the stress is not at all proportional to strain. ঠিক আছে, so তোমরা দেখতেই পাচ্ছ, the blue lines actually they represents lower yield strength of this specimen. So some material have lower yield strength, some material have higher yield strength and all. So এইভাবে for different material we can plot different stress strain diagrams which are of very very wide engineering applications. Coming to the brittle materials, lastly, brittle materials যেরকম ধরো glass, stone, concrete, এই ধরনের জিনিস actually they don't undergo any amount of plastic deformation. সেই জন্য দেখো just ওই তোমার elastic limitটা যেই cross করেছে, once it has crossed the elastic limit, there is nothing. There is failure of this specimen. So এইখানে যে তোমার plastic part টা ছিল, the plastic part that was there in a mild steel specimen or a ductile specimen, actually that portion is not at all there. So whenever you are encountering a brittle material, the stress proportional to strain, when the elastic part is only there is no plastic part of the specimen, plastic deformation part of the specimen. So it cannot, any brittle material that cannot undergo any amount of any amount of plastic deformation. Only necking ta hobei na, that necking or the reduction in diameter, there is no scope for that. Like glass, if you see, have you seen a glass to be like plastically deformed? A rubber band, you have seen that rubber band can plastically deform. You can see that there is a small kink or a small rupture occurring on the specimen. Still, the material can bear some amount of the load. But if you see a specimen of a glass, it cannot undergo even a minute amount of deformation, even a minute amount of deformation on its surface. Actually, it will fracture. Once the elastic limit ends, it will fracture by itself. And mind that the elastic part is also very small for for brittle materials and all. ঠিক আছে? তো এইটাই আমি একটু ডিসকাস করলাম। নেক্সট ডে আমি আরেকটা ফিগার দেখে একটু বলে দেবো, বা আদার বই থেকে একটুখানি আমি বলে দেবো। হ্যাঁ, এখানে এটাই আমার বলার ছিল, বেসিক্স গুলো এইটাই আছে। আর নেক্সট ডে আমি আরেকটু থিওরি বলবো, আর আরেকটু তোমাদেরকে আমি নেক্সট ডে আমরা ওই ইয়েটাই আমি আরেকটু ডিসকাস করবো, ওই ভিডিওগ্রাফি থেকে আমরা ডিসকাস করবো। তো আমাদের দুটো এক্সপেরিমেন্ট হলো, ডিসকাশন হলো। নেক্সট ডে আমরা ওই ভিডিওগ্রাফিতে আমরা এক্সপেরিমেন্টটা নিয়ে আরেকটু ডিসকাস করবো। ঠিক আছে? সো আজকে এটুকুই থাক। আচ্ছা, ভিডিওগ্রাফিটা তোমরা সবাই দেখছো তো?
হ্যাঁ স্যার।
এভরিবডি হ্যাজ গট দ্য লিংক?
Yes, sir.
হ্যাঁ স্যার।
অ্যাটেন্ডেন্স দেওয়ার সময় ছিল অনেকজন, কতজন? 13 জনই ছিল। অ্যাটেন্ডেন্স দেওয়ার সময় অনেকজন থাকে, ক্লাস শেষ হওয়ার পরে দেখি কেউই থাকে না, কি ব্যাপার? এখানে সিরিয়াল নাম্বার করলে মোটামুটি 20 জন তো হওয়া উচিত ছিল। যাই হোক, অনেকে বোধহয় চলে গেছে। ঠিক আছে, ইন্টারেস্ট না হলে করবে না, সেটা কিছু না। আচ্ছা, নেক্সট ডে তোমরা কি একটু প্রেজেন্ট করতে পারবে কেউ ইয়েটা, ভিডিওগ্রাফিটা? নাকি আমি তাহলে ডাউনলোড করে নিয়ে প্রেজেন্ট করব, কোনটা সুবিধা হয়? ঠিক আছে, তোমরা করলেও হয়, নাহলে আমি পারলে আমি আজকে দেখছি, আমি ডাউনলোড করে নেবো সবকটা। আমি ডাউনলোড করলে কি আমি কন্ট্রোল করতে পারবো, মানে কোন সবকটা পার্ট তো এসেনশিয়াল না, যেই জায়গাগুলোতে তোমাদের ডাউট আছে বা যেই জায়গাগুলো মোস্টলি বলার দরকার, সেই জায়গাটাতে আমরা একটু বেশি কনসেন্ট্রেট করব। ঠিক আছে? the parts that are mostly মানে ইম্পর্টেন্ট, সেই জায়গাগুলো আমি ভিডিওগ্রাফি গুলো you have seen like it's like কতক্ষণের, like 1 hour and all I think. হ্যাঁ, সো এটা চালিয়ে দিলে তো 2 hours এমনি চলে যাবে, 2 hours will be gone by that. So আমরা জাস্ট ইম্পর্টেন্ট পার্টস and mostly the parts where you find difficulty in, সেই জায়গাগুলো আমরা একটু ডিসকাস করব। আর যেহেতু তোমরা স্ট্রেংথ অফ মেটেরিয়ালস তোমরা পড়োনি, তোমরা তো স্ট্রেংথ অফ মেটেরিয়ালস এখনো পড়োনি আই থিঙ্ক, তাই তো? হ্যাঁ হ্যাঁ। সো আমি একটু আজকেই বলে দিতে পারি, বাট অ্যাকচুয়ালি সমস্যাটা হচ্ছে সবাই তো আমি দেখছি যে অনেকে লিভ করে গেছে অ্যাকচুয়ালি। সো সেই জন্য ঠিক আছে, নেক্সট ডে আমি না আরেকটু বিয়ার জনসনের বইটা থেকে আমি আরেকটুখানি ডিটেল করে বলে দেবো এই জিনিসটা, মানে এই যে কাপ অ্যান্ড কোন ফ্র্যাকচার এন্ড অল দোজ থিংস, যেগুলো আমি এখন ডিসকাস করলাম। আর ইফ ইউ ফিল লাইক তোমাদের যদি মনে হয় যে একটু ইয়ে করবে, তোমরাও একটু ওই বইটা একটু দেখতে পারো। ঠিক আছে, বিয়ার জনসনের বইটা যদি ফিল করো আমি পাঠিয়ে দেবো। তো ইউ ক্যান অলসো হ্যাভ এ লুক অ্যাট দি থিংস অ্যাকচুয়ালি, যে কিভাবে কি আছে, স্ট্রেস স্ট্রেন ডায়াগ্রাম কাকে বলে, হোয়াট ইজ হুকস ল এন্ড অল দোজ থিংস। আই হোপ এটা তোমাদেরও বোধহয় স্ট্রেংথ অফ মেটেরিয়ালস তোমাদের আছে না? আমি তো জানি এগুলো তোমরা জানো, মানে হ্যালো না তো
স্ট্রেস
স্ট্রেংথ অফ
স্ট্রেন
মেটেরিয়ালস
আছে, ওটা ইয়ের মধ্যে আছে, স্ট্রাকচারের ভেতরে ঢোকানো আছে।
আচ্ছা 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 আচ্ছা, ঠিক আছে, ওটা বোধহয় তোমাদের পরে হবে। ঠিক আছে, আমি অ্যাকচুয়ালি এটা মেকানিক্যালের স্লাইডটা তৈরি করেছিলাম, তো যেহেতু ওরা ওই স্ট্রেস স্ট্রেন ডায়াগ্রাম ইয়াংস মডুলাস অনেকটা জানে বলে আমি ওইগুলো আর অতটা ডিটেল করে এখানে দিইনি, বুঝেছো তো? আমি দরকার হলে আমি নেক্সট ডে তে আরেকটু ওই স্ট্রেস স্ট্রেন ডায়াগ্রামের জায়গাটা একটু ঢুকিয়ে আরেকটু ডিসকাস করে নেবো। ঠিক আছে, জায়গাগুলো সেটা হয়তো তোমাদের আরেকটু হেল্পফুলি হবে পরবর্তীকালেও।
ওকে স্যার।
ওকে, ঠিক আছে, তাহলে আজকে এটাই ডিসকানেক্ট করছি। কোনো কোয়েশ্চেন থাকলে জিজ্ঞেস করতে পারো, এলস ডিসকানেক্ট করবো।
हेलो सर।
हाँ बोलो बोलो।
सर ये why there is a upper yield point and lower yield point in stress strain curve, sir?
Mm-hmm.
Sir, why there are 2 points, sir, upper yield and lower yields? Why it cannot be a flat?
Why there is a
Upper yield point and lower yield point.
हाँ, there is the upper yield point माने क्या, जहाँ से yielding start हो रहा है. So once there is a start of yielding, and उसके बाद क्या होता है, there is certain amount of strain hardening actually. So that is why there is a lower yield point. The yielding actually ends there. उसके बाद there is a strain hardening part. ठीक है, the material suddenly gains its strength actually. माने ঠিক আছে, others can leave. যারা leave করতে চায়, others can leave. I'm also again presenting, মানে আমি আবার জায়গাটাতে একটু যাচ্ছি. যাদের হয়ে গেছে they can leave. So this part that you are asking, এইখানে দেখো আমি নেক্সট আরেকটু I will try to have a better figure of this one. So এইখানে দেখো this part actually. So this part is the upper yield point. ঠিক আছে, এই পার্টটা হচ্ছে upper yield point. ঠিক আছে, once it reaches the upper yield point actually there is a certain amount of strain hardening occurring in the material. ঠিক আছে, the material actually strain hardens. When any material if you try to deform it, it has certain internal resistance, so there is certain amount of strain hardening. So that is why there is a certain drop, and then suddenly it increases its strength. ঠিক আছে, there is a sudden increase in the strength of the material. See, it is able to again bear some load. মানে এই পার্টটা, if you see this part, so if I call it C and if I call it D actually, so for the part C to D actually, the material actually you can see that there was a reduction in the load actually dropped, but still there was an extension in the specimen. ঠিক আছে, so there is a reduction in the strength of the material, but after the point D actually there is again a sudden increase in the load, so it is again able to bear this amount of the load. So there is a sudden, again there is a strain hardening part, there is a like the material is able to strain harden, or it can actually bear certain amount of more load actually. So the point where the necking or the plastic part started, we call it as the point C, the upper yield point. Then again it drops actually, so it has started to deform plastically, so it is losing strength. So you can see that the curve is actually drooping from the point C to D. The curve has actually drooped. ঠিক আছে, you are increasing, there is decrease in the load but increase in extension. You are not applying any load, but still the material is material is having some extension. But once you cross the point D, the material actually regains its strength. So that is why this is called the upper yield point, upper deformation part, and this D point is called the lower deformation point. But lower point actually, after which the material will again gain some strength. C is the point where the material starts losing strength. It starts to deform plastically. And D is the point after which the material again gains some strength due to strain hardening. So that is why the C is called the upper yield point, D is called the lower yield point. After the point D, again there is some strength coming back inside the material due to strain hardening. ঠিক আছে? So that is why it is called the lower yield point. The material recovers after the point D. It recovers to certain extent after the point D. এই যে পয়েন্টটা, if you see the point C, but still there is extension. How can that happen? Because the specimen is deforming. The specimen has already started rupturing. It is losing strength. But after the point D, you can see that again the curve goes up. So it is able to withstand certain amount of load actually. ঠিক আছে? So D is the lower point up to which the material deforms. Then again there is a gain in strength, and the point comes when the material actually ruptures. ঠিক আছে? It reaches a certain ultimate value, and after this it ruptures. Ultimate strength, and then it ruptures. ঠিক আছে?
Okay, sir. Thank you.
I think this is due to the ফিগারটা একটু ক্লামজি হয়ে গেছে. The figure is due to the clumsy, এর জন্য আমার একটু বোঝাতেও অসুবিধা হচ্ছে. So if you just allow me on the next day, আমি নেক্সট ডে এটা কোনো বই থেকে তোমাদেরকে আরেকটু বেটার করে আমি এক্সপ্লেন করে দেবো, বা I have to get hold of a good picture on that one. ঠিক আছে? So just allow me one day, next class এটা actually আমি যেহেতু it's part of the mechanical curriculum, আমি এটাকে আর include করিনি. Just from the B.R. Johnston I am taking 1-2 minutes more. So you can see এইখানে দেখো, you can see. ঠিক আছে, low carbon steel, it's a mild steel, it's a brittle material, it's a ductile material. So you can see the material actually dropped. Then again there is a strain hardening part, a huge strain hardening part. I hope you can see, right?
Yes, sir.
Hello? So there is a huge strain hardening part. So that is why you have an upper yield point where the material actually started to lose strength, the curve drooped. So there is lowering of force, but there is deformation. And there is a point up to which it will droop, and after that again it will go up. See, there is a huge strain hardening part. So the point from where the strain hardening point starts, that is known as the lower yield point, and the point before that is known as the upper yield point. ঠিক আছে?
Okay, sir.
ঠিক আছে. সো আমি ডিসকানেক্ট করছি, আই এম ডিসকানেক্টিং। আর কোনো কোয়েশ্চেন আছে? এনিথিং মোর? ওকে, so I'm disconnecting, huh? Thank you.